point. All right, now for something technical. So one of the hardest things in C of late is dealing with things like memory and pointers and malloc and free. And increasingly, will this be an opportunity to really screw up your programs and make programs that crash and segfault and core dump. But thankfully, just as we have tools to write programs, we also have tools to fix or to diagnose or debug programs. We've used, or we've said you should use, GDB thus far, the GNU debugger. But we also introduced this week a nice tool called Valgrind, whose purpose in life is to analyze your code and figure out if you've screwed up with regard to memory management. Did you accidentally leak memory? Did you accidentally go beyond the boundaries of some array? Now, the tool is imperfect. It can't necessarily perfectly test your code because, of course, anytime you run programs, you give them input. And Valgrind is not going to be able to try your program on an infinite supply of input. So it's going to do its best guess. But you'll find that it can help us find some things quite nicely. Let me go ahead and open up a file called memory.c. That's among our source code for today. And this is a pretty stupid program that's deliberately buggy in that it does the following. So let's start from the bottom. Here is my main function. Takes no command line arguments. Apparently calls a function f and then returns 0. So that looks OK. But then let's scroll upward to the f function. It returns void. It takes no arguments in. But it does, in this first line, call malloc. And just as a check, sanity check, how many bytes get malloced in this highlighted line? So 40, right? If we assume an int is 4 bytes, then 4 times 10 is, of course, 40. And then what, just to be technical, are we storing in x? An address, the address of that chunk of 40 bytes. So that's sort of from 2 weeks back. And then on the next line, unfortunately, I do something stupid. Why is this flawed, this second line of code? X bracket 10 gets 0. Yeah. Perfect. So the maximum index for this array should be 9, from 0 through 9, because I've only allocated 10 ints. So of course, this is an off by 1 error, or I'm overreaching the boundaries of my array. In the worst case, this program might crash and segfault and core dump, but not always. And that's one of the frustrating things. Often, if you just go ever so slightly outside of your memory bounds, your memory's bounds, the program might not actually crash, because the operating system is being a bit generous and is allowing you, if unofficially, and in a dangerous way, to go slightly beyond your array's bounds. So in other words, this is kind of hard to catch sometimes, certainly just by visual inspection. So let's instead try this. Let me open a terminal window. Let me go ahead then and compile my code with make memory. And now if I run this program, it actually seems to be fine, right? No core dump, no segmentation fault. So at first glance, all is OK. But now instead, let me run this new program, Valgrind, and let me go ahead and run it on memory. I still need the / to say test this program here, and then hit enter. Unfortunately, whoever first wrote Valgrind decided that let's make its output a crazy mess. But if you read between the lines, you can actually see some juicy information. So let me scroll back up to the very start of this. And you'll see here's where we started. This is where I ran the command. And now we have some copyright information and stuff like that. But here's where the helpful information is. Invalid write of size 4 at such and such an address. Now, these pointers, these addresses on the left-hand side, are generally not all that useful unless we really get low level with our debugging. But it does mean that you did something wrong at that address, specifically at line 23 of what file? All right, so memory.c, right? So the output is actually quite similar to GDB. And so if I go back to line 23, which is this guy here, sure enough, Valgrind has noticed that I wrote 4 bytes erroneously there. Now, it's still up to me, the human, to determine where is my mistake. And of course, we already identified the mistake. But the program found it, even though when I ran this program, nothing appeared to be wrong. Now, lastly, this here says it's actually being addressed as 0 bytes. Actually, that's OK. Let me scroll down here. And now if we go down here, leak summary, definitely lost, 40 bytes in one block. Now, this might be a much bigger program. Right now, it's pretty simple. It's only a few lines. So I can actually run Valgrind with more switches. And notice it's telling me to rerun with -- leak -check equals full to see details of leaked memory. And in fact, if I go back to my slide here, what you should generally run, even though it's a little tedious to type, is exactly this. Valgrind -v. So I'm going to try this. Valgrind -v. -v almost always means verbose for a Linux program. Some of these switches take hyphen, not single hyphens. The convention, just FYI, is if it's a single letter switch, it's usually a single hyphen. If it's a longer word like leak, then you would actually use hyphen, but that's just a human convention. So leak check equals full. And then I have to say a.out in general, but in the concrete case, it's the program called memory. So let me hit enter now. And oh my god, so much more flew across the screen there. But let's scroll up, and here we go. Now, because I ran it with more verbose output, and I frankly knew where to look. You would kind of have to take a few seconds to sift through this. But notice, 40 bytes in one block are definitely lost in loss record 1 of 1. I don't quite know what that means, but it looks like the bug is in a function called malloc. Right? So probably not. Right? So you've called malloc. So let's at least chase this bug back a little further in the stack. And what was the previous function called? OK, it's probably me who screwed up. So somewhere in memory.c, line 22, a function called f was called. And somewhere in there, 40 bytes were lost. Of course, in a program this small, it's pretty obvious to the reader what I did wrong, which is what? How did I lose these 40 bytes? I didn't call free, right? I should have called free at some point. And of course, this would be kind of a silly exercise to just do it now, because this is, again, kind of a bogus program. But that would be the correct fix. Just hopefully in the real world, if I'm writing some real program, there would be some useful stuff going on in between those lines. But this one is just completely wrong. Going into bracket 10 is just incorrect. So in short, unglamorous program, but a useful tool. So henceforth, anytime you write any program, whether for pset 5 or onward, that uses malloc, that uses arrays in any way, do run your program through that tool. Take a few seconds to sift through the output, and it might find a bug, frankly, before your TF does. Any questions? All right. So now we have the opportunity to start to implement, with these same fundamentals from the first half of the semester, some real-world constructs so that we can begin to solve more interesting, more challenging problems with more sophisticated tools than just an array or variable. So this is a photograph from my favorite house, Mather. And this is, of course, a stack of trays. Well, it turns out in computer science, a stack is a data structure. It's a data structure that allows you to actually store data in potentially a more useful way than, say, a simple array does. The idea of a stack, just like in the real world, is that if you have a stack of trays, there's some upsides and some downsides. One upside of a stack is that if I put something down, like a tray, and then I put something else down, like a tray, then I put something else down, like a tray, well, it's very easy and very fast to get the most recent thing from that stack. You can just pop it off the top of the stack, so to speak. Unfortunately, a stack of trays or a stack of paper here is not the most efficient system if you instead are, for instance, queuing up for something you really want, right? It would kind of suck if you got to the Apple store at like 5 a.m. before, or you got even earlier, to get your fancy new iPhone 3 or 4 or whatever, and the staff in blue shirts starts popping people off the queue from the back, right? That is a data structure, a bad design when it comes to selling iPhones. You would really piss off the people at the front of the line. So instead, in computer science, there's an alternative data structure that's similar in spirit. It's kind of a list of some sort, but it's called technically a queue. And a queue is first in, first out. So the acronym is FIFO, F-I-F-O. First in, first out just means if you get there first in the morning, you're going to be the first one allowed to buy that product. By contrast, a stack is the opposite, but we'll see utility of both of them. In fact, those of you familiar with HTML know that prevalent in HTML is the idea of balancing tags, having an open tag and a closed tag. And the notion of validating HTML involves checking. Did you close all of the tags that you opened? Well, you can actually use, it turns out, a stack data structure to answer questions like that if you're the W3C's validator. Now, for those for whom most of those words made no sense, not to fear, in just a couple of weeks, we'll be diving into the web programming portion of the course. But to begin to now use these data structures and solve more interesting problems, we need to be able to chain structures together. One of the biggest problems of an array is that even though it's super simple to use once you get the hang of it, and that you can go to any element in it, what can you not do easily with an array? Sorry? You can't extend it, right? You have to decide in advance if you want 10 bytes or 100 bytes or whatever it is that you're allocating. You have to decide in advance. And what happens if you decide, oh, I really need one additional element or twice as many elements? What do you have to do if you're using arrays to store your data? What's that? Yeah, you pretty much have to make a new one, copy the old data into the new one, and then free the old one. Now, we haven't done that ourselves really, but we've been using something that does. What function that we've been using since week 1 does exactly that. When it runs out of space, it allocates more, copies old into new, and then frees the old. GetString, exactly. Remember, GetString is a perfect example because we have no idea how long of a sentence or a paragraph some student's ever going to type when we sit down at the start of the semester to implement GetString. So we have to be dynamic. We have to enable the function to grow the storage space it's using. And we've seen as of 2 weeks ago that the technique for that involves using malloc. And it turns out some other related functions like realloc and the like, but it boils down to allocating and reallocating memory. So what if there were a data structure that allowed you to have some fixed amount of memory at first, but then grow it super easily? Because the problem with using the array trick is what? If your string is this big and you need 1 more byte or twice as many bytes, this is a lot of work, right? You have to ask the operating system for more memory. So temporarily, you're doubling your memory footprint. Then you have to copy, as in a for or while loop, all of the old memory into the new memory. Then you have to free that memory. That's a lot of steps if the user has maybe hit 1 extra character. So what's an alternative? You can avoid resizing arrays in this manner by just allocating maybe 2 gigabytes of memory. Anytime the user might type something in, well, just choose a huge upper bound, 2 gigabytes. But of course, what's the obvious problem here? Right? If you just allocate an excessive amount of memory, your program at some point is just going to stop working. Or it's going to slow the computer to a crawl because it appears to be using way more memory than it should. And if you only have a couple gigabytes of RAM and your silly little program is using it when you're actually trying to do useful work with like a browser or word processor, everything will just slow to a crawl, as we've discussed. So suppose there were a structure